We're in section 10.3 and we're looking at MOSFETs. And MOSFET is an acronym for metallic oxide semiconductor field effect transistor. And isn't that a mouthful? A MOSFET is fabricated differently and operates differently than a JFET, but it does have some similarities. There are two classes of MOSFETs. There are depletion mode and there are enhancement mode. Each class is available as an N or a P channel, giving a total of 4 types of MOSFET. So depletion mode comes in an N or a P, and enhancement mode comes in an N or a P. So we have 4 different types of MOSFETs. The first one we'll look at is the depletion mode MOSFET. Note, continuous channel of N-type material between the source and the drain. So you'll notice here is the source, here is the drain, and we have a continuous channel of N-type material. A voltage placed across the source and drain would induce current flow. So if we put a voltage in between the source and drain, we would have current flow. The channel acts like a resistor, and this is very similar to what we saw in a JFET, and a negative voltage will reduce current. So if we put a negative voltage here, it will tend to increase the resistance of the N-type channel, and that would reduce current. A more positive voltage would cause the channel to reduce in resistance and conduct lots of current. The gate is connected to aluminum, which is insulated from the channel by a thin layer of silicon dioxide. So here we have our gate, and this is where we differ greatly from a FET, is that we have actually a metal here. This is aluminum, and the aluminum is insulated from the channel by a piece of silicon dioxide. So what that's going to do is there's no electrical connection between the gate and the N-type material because we have an insulator in between them, but we will be able to induce an electronic field through the material, but there is no connection between the gate and the source and drain. Okay, the 3 layers led to the device name, hence we have metallic, oxide, semiconductor. So these 3 layers led to the device name, and here we have the actual schematic symbol. We have a gate, a drain, and a source, and it's usually connected as 3. However, there is an option for a 4th connection, and that would be over here. This would just add to a little bit additional more control. Our main concern is going to be with the 3 connections. Okay, this is the P type. Okay, this is the same as N except for the reversal of the material. The line with the arrow also indicates the connection between the source and the drain. Okay, that's right here. And again, same thing except that materials have been reversed. Okay, depletion mode MOSFET. In a depletion mode MOSFET, there is a continuous channel of N-type material between the source and the drain terminals. With a voltage applied, current can easily flow between the terminals. The metal gate of the MOSFET is insulated from the substrate by a layer of silicon dioxide. Enhancement mode MOSFETs. The source and drain terminals connect to heavily doped N-type silicon in an N-channel enhancement mode MOSFET. So here we have the source, here we have the drain. They're connected to heavily doped N-type material. The area between the source and the drain is lightly doped P-type material. So there's no continuous channel between the source and the drain like we had with JFETs and with the depletion mode. And remember, this is enhancement mode. This is the major difference right here. Okay, a proper polarity gate voltage must be applied for current flow. Okay, so we're going to need a gate voltage to get current flow, and we will address that in a few slides from now. A broken line in the schematic symbol indicates that there is no continuous path from source to drain. So when you look at the schematic symbol for an E-mode MOSFET, you'll notice that usually you'd have a continuous line here, as we did with FETs and the depletion mode, but here it is broken, and is broken because there is not a continuous channel. Okay, MOSFET biasing and operations. The resistance of the channel in a FET depends upon doping and the physical dimensions of the material. In a MOSFET, the effective doping level is modified by, and notice this, by the biasing. So we're going to look at the biasing in a depletion mode and an enhancement mode, and we'll start out with the depletion mode. So if an external DC source is connected between the source and drain of a depletion mode MOSFET, measurable current will flow, notice this, dependent upon the value of the channel resistance. So what are we saying? Here we have the source, here we have a drain, and here a voltage is applied through a resistor. And we will have current flow through the channel. Now, the amount of current flow will be dependent upon the resistance of the channel, and we're going to find that that's going to vary. By making the gate more positive than the source, an increase in source to current drain will occur. Okay? By making the gate more positive than the source. Okay, excuse me. So here we have our voltage source, and there's an interesting thing that takes place in a MOSFET. Notice we have the metallic material right here. It is separated from the N-type material by the insulating silicon dioxide. Then we have the N-type material. Well, this acts as a capacitance, and the silicon dioxide, in effect, is the dielectric material, and the metal here is one side of the capacitor, and the N-type material is the other side. As we apply a positive voltage here, what will occur is that we'll have a positive charge on this side, we will have a negative on this side. The negative here will represent free electrons, and this will take that N-type material, adding many more free electrons. It will be like heavily doped N-type material, and it will easily conduct current flow, and it will have very little resistance to current flow. Now, in the second scenario, if the gate is made more negative than the source, the channel of doping is effectively reduced, slowing current flow. And so here, and this picture is the same as this, except that we have changed the biasing on the gate. And so now we're putting a negative voltage on the gate, and we're having that same capacitance effect, except that now the electrons are on the top plate, and we have a positive charge on the bottom, and this effectively reduces the doping level in the N-type material, and depending on the amount of negative voltage, this will become extremely resistive, and it will impede current flow. So, in the depletion mode MOSFET, the charge on this capacitor ultimately determines how much current is going to flow through the channel. Now, in an enhancement mode MOSFET, when a positive gate voltage is applied, the gate capacitance charges to the value of the gate source voltage. Now remember, actually in this drawing here, this N-type material is not continuous. It's kind of like this right here. But again, we're placing the positive voltage, and again there is that capacitance phenomenon. And here we have the negative charge, or the positive charge on the top plate, if this is a positive voltage. And then we have a negative charge. Now the negative charge here is not in the P-type material. Actually, the negative charge is right along the edge of the silicon dioxide. And what this forms is what's referred to as an N-type inversion layer. N-type inversion layer. It's not truly N-type material, but it's referred to as an N-type inversion layer. And this thin layer is right along the edge of the silicon, and it will be heavily electrons. And so what will end up happening is that this will cause current to flow along the edge of that silicon dioxide, and we will have current flow, and that is with a positive voltage on the gate. Now, when we do just the opposite, and again this is the same thing except that now we have a negative voltage here, the capacitance, again the charge, the negative, the electrons will be on top, the positive charge will be along the bottom, and this will effectively cut off current flow. And so there will be no current flow because there is no path at this point, there's no N-type inversion layer. And so we have this positive into P-type material, and we will cut off current flow, and now there is an incomplete channel, and it will be cut off. Okay, this has introduced the depletion mode and enhancement mode MOSFET devices, and we've also looked at the biasing of both devices.